In this study, the spring mass approach was used to describe the overall response of a slender cantilever beam, which undergoes the projectile impact. The indentation phenomenon was neglected because the overall beam deflection reached large displacement during the impact because of the composite material property. In that way, the projectile mass was added to the beam and the structure stiffness was the flexural beam stiffness. The nonlinear vibration theory allows to establish the correct dynamical behavior, and the analytical model was validated through experimental tests. At the end, the boundary conditions belonging to the low velocity impact were imposed on the analytical model and was compared with a numerical simulation. First of all, we analyzed the Beckman curve of the first two modes. The first nonlinear frequency has hardening behavior, so the frequency increases with every vibration amplitude. On the contrary, the Beckman curve on the second mode is softening type. The nonlinear behavior of the first frequency affects the response of the beam during the impact. Following the spring mass theory, the first half oscillation of the system describes the impact dynamics. So, the time of the impact can be reduced or augmented in function of the hardening or softening trend in nonlinear frequency. Likewise, you can evaluate the impact velocity in function of the maximum impact deflection. The natural frequency obtained by the analytical model was compared with the numerical model. Then, the early stage of the impact was evaluated to verify the flexural wave speed. In order to assess the capability of the analytical and numerical model, a comparison between the two models' results were evaluated. The deflection computed with the analytical model overlaps the numerical one. The impact time is perfectly described, as well as the maximum deflection. Also, the analytical trend of velocity is consistent with the numerical one. However, the analytical signal appears smoother than the numerical solution.